Hi, my name is Haizheng Zhong. I'm an associate professor of School of Materials Science and Engineering at the Beijing Institute of Technology. I'm also a faculty member of Beijing Laboratory of Nanophotonics and Ultrafine Optic Electronic Systems. My current research consists the study of semiconductor nanocrystals for light emitting and solar harvesting applications. Recently, we published a perspective paper on GFC lighters. This perspective highlights recent progress on tuning the luminescence property of 136 semiconductor nanocrystal, especially focus on the synthesis spectroscopy properties, as well as their applications in light-emitting devices and bioimaging techniques. Although 2,6 cadmium-based and 4,6 lead-based semiconductor nanocrystals have been the focus in the past years, they have limited future because of the well-known toxicity. Group 136 semiconductors combine Group 1 copper or silver, Group 3 aluminum, gallium or indium, and Group 6 sulfide selenium tellurium elements are known as the analogs of 2,6 binary compounds and have been identified as potential less toxic materials. These compounds cover a wide range of optical and electronic properties, but are related to each other for their calcipride structure. The synthesis of 136 semiconductor nanocrystals was developed by adapting the understanding that learned from 2,6 nanocrystals. Basically, there are mainly two routes to fabricate luminescent 136 nanocrystals: hot injection and non-injection methods. To explore the potential of 136 nanocrystal as light emitters, it is very important to understand their luminous mechanism, learn their factors that influence their luminous properties. 136 semiconductor nanocrystals have been studied by steady and time-resolved photoluminescence spectra. In comparison to the 2,6 cadmium-based nanocrystals, these nanocrystals exhibit several particular properties, such as broad emission peaks, large Stokes shifts, and longer PR lifetimes. The spectroscopic study also indicates that the PR spectra of 136 nanocrystals are wavelength and excitation energy as well as temperature dependent. All of these features can't be explained by the exciton recombination mechanism, but also suggest a donor acceptor mechanism.
According to the discussion above, we found that intrinsic and surface defects play an important role in luminescence process. So we can finely tune the emission spectra and photoluminescence quantum yields and other luminescence properties of 136 nanocrystals by applying a combination of size, composition, and surface tune strategies.
It is very exciting to study their fascinating properties and explore promising applications in optoelectronics and biotechnology. Now I will show you the S-paired wide LED in our laboratory. This S-paired wide LED combines yellow, green, rare earth phosphorus with red copper indium sulfide nanocrystals. Recent works have demonstrated that copper indium sulfide nanocrystals could be very excellent converting materials for wide LED applications. Some performance of wide LED can be improved by using red copper indium sulfide nanocrystals.
I really hope this perspective can be useful for your research. If you are more interested in our perspective, I encourage you to read our perspective in Journal Physical Chemistry Letters. I'm very grateful to the editor of Journal Physical Chemistry Letters for the invitation of our perspective on such a topic. I would also like to thank Professor Yunfang Li and Professor Greg Scholes for their support on my previous work on such a topic.